Okay, in this screencast, we're going to look at problems 735 and 736 from Mastering Physics. They're work done by a variable force. What that means is an external force is doing is acting on an object. We don't know what the object is, but it moves the object a certain distance, and we can calculate the work done by the area under the graph. This isn't too much different than what we've seen before with a spring, right? When you guys did your Hooke's Law spring lab, you found that force versus displacement, you got a graph that looks something like this, and we figured out that the area under this graph was the energy stored in the spring. Well, that stored energy came because an external force compressed the spring. When I was standing in front of the class, it was my fingers squeezing that spring down. So as I exerted a force on that spring, I was doing work on the spring. So I was if the spring was the system, my force, my fingers were an external force from outside the system transferring energy into the system through working. So the work I did was exactly equal to the area under the graph, which was the energy stored in the spring. So the same idea here. We basically have three areas here, and it asks us how much work is done from x equals 0 to x equals 0.75 meters. So basically we're just going to find the area of this rectangle, the area of this rectangle, and the area of, we'll say this one right here. Okay, so area 1 plus area 2 plus area 3 is the work that was done on that object. 0.25 times 0.6 is 0.15 joules, I believe, plus 0.25 times 0.4, that is 0.1 joule. And then I got that second 0.25, by the way, from here to here. So the base of that rectangle times the height of the rectangle, which was about 4. This rectangle has a height of about 0.8 times 0.25, so that is 0.2 joules. So if I add all that up, I get 0.45 joules. So let's see how we did on that one. It's always good to check your work here. Okay, how much work is done if it moves the object from 0.15 to 0.55? Okay, so now we're starting somewhere in here and we're ending somewhere over here. So it's a little bit different. So for this one, I'll use a different color. It starts at 0.2, which is somewhere, we'll call it about right there. Or no, 0.15, sorry. 0.15. So that's 0.15. And it goes to 0.55, which is just on this side of the transition here. So now I've got just a thin sliver of area here at the higher force of 0.6 newtons, and then I've got the whole blue area right here in the middle, so that's 0.1 again, and then I've got this tiny sliver here at 0.8 newtons. It moves it for 0.5 for basically 0.05. So for part B, I'm going to say the difference, the base of this rectangle here is from 0.25 to 0.15. So the work done is equal to 0.25 minus 0.15, so that's 0.1, times the force for that portion of the graph is 0.6, plus the area of this rectangle right here, we already know that is the 0.1 joule, plus 0.55 minus 0.5 times that force, which was 0.8. So let me do that on a calculator real quick. I'm just going to pause it and take it off screen for a minute. So what I just came up with was 0.2 joules. Let's see if we got that right. Okay, so that's problem 735. Actually, I have to go to the previous problem for 736. It's a similar problem, work done by a variable force. So instead of telling us the beginning and ending points, now they're giving us the beginning point, and the work done on it is equal to 0.21 joules. Okay, so if the initial position of the object is 0.40, it's somewhere in here, and the work done on it is equal to 0.21 joules. So I'm going to go ahead and copy this to my page here. I'll go offline for this, so you don't have to sit through that. Okay, so now this problem is asking for if the work done is 0.21 joules and it starts at 0.4, what is the final position? Well, again, we're going to use the area under the graph, knowing that force times that displacement is equal to the work done on the object, if it's a spring or whatever the object is. And that is xf minus xi. That's what delta x is. So if it's a positive value of 0.21 joules, I know the final position must be larger than the initial. So it must be over in this direction over here. So the first thing I'm going to do is see how much area is under this part of the graph right here, and see if my 0.21 joules is made up of just this portion of the graph, or if I have to go some amount into this portion right here. So this is at 0.8, this is 0.1. 0.8 times 0.1, that area, oops, sorry about that, times 0.1 is equal to 0.08 joules. That doesn't get me there. So I know it's got to go into this portion of the graph right here. How much area is under here? 0.25 times 0.4, that is 0.1 joules of area right there. So I add 0.08 plus 0.1, and I'm still not at 0.21 joules. So I know I've got 0.03 joules somewhere over here left to go. Where did I get that 0.03 from? It's 0.21 minus 0.18. That's how much area is left, how much work I need to find that was done by this force. Now it's down to 0.2. Okay, so my area is equal to 0.03, and it's equal to the base times the height. So base times height, and that is equal to, the height is 0.2 times whatever the base is. That's going to be the distance from the 0.75 point right there. So divide 0.03 by 0.2. Let me see what I get on my calculator. It's 0.15, right? 0.15. So my base is, sorry about that, undo a little stray mark there. So the base of that rectangle is 0.15 meters. That means this distance here is 0.15, so that must be 0.90, because that's 0.75 plus 0.15 is 0.90. So the final position would be 0.90 meters, because that's going to give me just the right amount of area here, 0.03 joules. This was 0.08 joules. Okay, so the area under the graph again would then have to add up to 0.21 joules. Just to double check that. Let's see if we're right. Okay. What's the final position? If its initial position is 0.40 and the work done is negative 0.19. Okay? So the work done is negative 0.19. Well, if the work done is negative, I know my final position must be a larger number, must be a smaller number than my initial position. So in other words, my final position is going to be somewhere over here. So if I go in this direction, I'm going to get negative work. If I go in this direction, I'm going to get positive work. So it turns out that I'm going to follow the same exact process, but I'm going to go in this direction until I get an area under the graph equal to 0.19 joules. So I'm going to start at 0.40. I'll add up the area getting down to 0.25. That would be 0.15 times 0.8. That's going to be 0.12 joules. That's not enough. So I know I've got to go over to this side a little bit. And I would do the same process that I did right here. I don't think I need to repeat that. Hopefully you understood how I got the 0.90. This is just going in the opposite direction because I've got a displacement of x where the final position is going to be smaller than the initial position. Now, notice that I've got this formula here, but because the force isn't constant, I can't just substitute in, my final position of 0.90, for instance, in the first half, and my initial position of 0.40, because the force isn't constant over that entire duration. It's changing. So I have to apply this formula in the various blocks that have a constant force. So I kind of split it into individual pieces. Okay, hope that helps you, and if you have other questions about mastering physics, let me know, and I will go ahead and record some more solutions for you. Thanks.